This is third lecture in the lateral equations, and in this lecture we will study the flight in a steady bank 10, and especially the ultimate question is how to determine the deflection angles for the control surfaces. And okay, so let's go to the first slide. Now we have the aircraft flying into the screen, and so the bank angle is phi, and apparently if we have a top view, the aircraft is turning clockwise. So we have the weight, gravity force, mg, and the lift force. Apparently it's not in equilibrium, so the forces are not balanced. In a correct bank turn, there should be no side slip. This is different from the previous lecture, only steady side slip, which means the aircraft is approaching or landing under crosswind. So what we have to make the aircraft in equilibrium is a centrifugal force. So if you compare the force diagram, can you find the difference between this graph and the one when we have in the analysis of the steady side slip? Okay, so in that case, in a steady side slip, the horizontal force is produced by the side slip angle. Okay, so in order to analyze the forces, we have the vertical force, and so it's a vertical component of the lift, which should be in balance with the gravity, and also the horizontal force, that's a horizontal component of the lift, which is equilibrium with the centrifugal force. Okay, and apparently now we can have the bank angle tending phi equals v squared divided by gr. So and we can easily determine the bank angle if we know the speed and the radius. Okay, so now we know the bank angle for the bank turn. So the question, I put a question here, what about the force acting on the pilot? So in order to answer this question, and I'm introducing a kind of new concept, that's a G-force. Perhaps you already heard of it earlier, especially when you hear, for example, the space launcher, and the G-force acting on the astronaut is pretty high, and the higher the more discomfortable. Okay, so let's continue with the G-force. That's kind of diversion from the main topic. And according to the previous analysis, we have the vertical component of the lift equals gravity. And if we do this, L divided by W, W is the weight of gravity, and the ratio is 1 over cosine phi. And now we define dimensionless acceleration or load factor, and we can have n equals 1 over cosine phi. So 1 over cosine phi, phi is the bank angle. We can determine the load factor. So what about G? So it's the so-called G-force. Where the G from? And let's answer this later. If now, as an example, if now the bank angle phi is 60 degrees, so cosine phi is 0.5, then we have the load factor of 2, which means the lift force acting on the pilot or passenger is twice of the gravity in order to make it in a steady bank turn. So in that case, if we move the G towards the right hand side, we have 2G. That's a so-called G force. So it's twice of the acceleration. And if the bank angle becomes 80 degrees, only slightly change, 20-degree change, and then the load factor becomes 5.76. So it's significant change, although the bank angle change increase is not so significant, but the load factor G-force increases significantly, which causes significant discomfort for the pilot or passenger. Okay, so in a high G bank turn, the lift also increases, and at a certain point it will approach to its stall point because CL changes increases with like in here is a virtual angle attack. So high G bank turn is also very dangerous. Why? Because the aircraft may soon enter stall. So that's why we need, on one hand, it's not comfortable, but also on the other hand, it's dangerous because it might stall the aircraft. Okay. Now let's address another issue, time to complete a turn. So how to get the time to complete a turn? And so I have a diagram in here. It's a top view of the turn, and you can see a circle, complete circle. And so time to complete a whole turn, that's 360 degrees. The circumference is a distance, so it's L equals 2 pi r. So that's a distance, and the aircraft will travel. Okay, then the time is 2 pi r divided by the velocity v, true airspeed. And to be more general, if the turn is only 5 per se radian, and then we just times the ratio per se divided by 2 pi, and eventually becomes per se r divided by v. Okay, so let's see whether we can walk further with r and v. Okay, in the force analysis, we know tan in phi, that's a bank turn angle, and equals mv squared divided by r divided by mg. So we have r is v squared divided by g tan in phi. Okay, so if we plug in r, and then the t can be per se v divided by g tan in phi. Okay, let's walk further, and we know L equals load factor times W, the weight, and also on the other hand, L equals the lift coefficient times half rho v squared times s. So we make them together, and we can have the velocity equals square root 2nw divided by rho scl. Okay, and also we know n equals 1 over cos phi, and we do some manipulation, we can have tan in phi equals square root n squared minus 1. So all these are known, and then we can replace plugging v and tan in phi into the t equation. So eventually we know the time used to complete a per se angle turn can be calculated with this equation in a red box. So instead of calculating through r and v, now we replace the r and v with n, load factor, the weight, and also cl, which can be easily accessed. Okay, so the answer I pasted in here. And now let me introduce another important thing, the rate 1 turn, which makes pilots the bank turn more comfortable. So a rate 1 turn is defined to be 3 degrees per second, or you complete entire circle turn in 2 minutes. That's a so-called rate 1 turn. And so a good rule of thumb, a quick estimation for the bank angle on the rate 1 turn is about 15% of true airspeed in knots. The unit should be knots. For example, if the velocity true airspeed is 100 knots, the bank angle is about 15 degrees. So should be no larger than 15 degrees for rate 1 turn. So that's a rule of thumb. And so from earlier, we know v squared equals gr tan in phi, and then we can introduce the rotation rate for the aircraft, which is can be calculated by v divided by r, and then we can have this. So this is rotation rate of the turn, and we are using the next slide, especially when we derive the deflection angle. So far, we get a kind of diversion. We introduce the load factor N or GForce, and eventually we come to the rotation rate. We're still looking at the bank turn, and we already know that the aircraft has a rotation rate during a steady bank turn, so it's pointing downward. And since this omega is pointing downward, it will produce two components, one along the wing, one along the vertical tail, but it's their directions are shown in the graph. Okay, so the Q component equals omega times sine phi. Phi is a bank angle. The other one R is omega times cosine phi. Okay, so for Q, and now we are taking out the right hand, and so the sum of your right hand points aligned with the arrow of Q, and we know, so this Q rotational rate is relevant with a nose-up pitch, and in that case, we need to have a downward movement of elevator, or elevator moves downward, deflects downward. Okay, similarly, we're looking at R and yawing rate. And again, take out your right hand. So the sum follows the arrow. And so this R is relates with a nose towards the right yaw. And in that case, the ruler need deflects towards the right. So I'm indicating the deflections of the rotor and elevator. And simultaneously, you need to have the aileron deflections to produce such a bank angle. Okay, so now we can write down the governing equation. Since it's a steady bank turn, for the rolling moment equation, we have LR times R, L delta A times delta A, L delta R times delta R. So there are three contributions. One contribution is from the yawing rate, and second contribution is from the aileron deflection. The third contribution is from the rotor deflection. And similarly, we can write down the yawing moment equation, just replacing the L by N. Okay, so that's the governing equations for roll and a yaw. And you may wonder what happens to the pitch. We will see that later. Okay, so you can see there are three contributions to the roll equation and the yaw equation. Okay, and apparently the elevator deflection is not considered. Why? Because elevator deflection is mainly contributing to the pitching moment. So that's why it's not contributed in here. Okay, so I'm pasting the two governing equations in here, and we can write them in a matrix form. And we are familiar with this, and in a previous lecture for the steady side slip, and we already have this, and so it's kind of straightforward. We just find the inverse of the coefficient, and then we can get the answer. But there's another approach. We can do the simplification by considering the secondary effect. And in this case, we can consider L delta A much larger, far larger than L delta R, because delta A is aileron deflection. Aileron is in charge of the rolling, right? But rotor is in charge of the yaw, so that's why the rolling moment contribution from the aileron deflection is much larger, and also the rotor deflection contribution to the rolling moment is negligible. The same for the N yawing moment, because aileron deflection and contribution to the yawing moment change is much larger than the aileron deflection. Okay, so then we can simplify the governing equations into such explicit relations, and apparently we can have delta A and delta R. That's quite straightforward by considering the secondary effect. Okay, so now let's write down the pitching moment equation, and that's much easier than the yawing and the rolling equation. And it has two contributions. One contribution is from the pitching rate. The other contribution is from the elevator deflection. So, and it's an explicit expression for elevator deflection, and I'm not reading it. It's showing in here. Okay, And so far, we have all the 3 deflection angles determined for a steady bank turn. And I hope you can understand the derivations and especially the secondary effect. Okay, so for the bank turn, it's kind of scattering. The knowledges are scattering. And we first studied the force analysis, and then we introduce the G-force or load factor N, and then we derive the equation, derive the rotation rate, expression for the rotation rate, and finally we determine the deflection angles for aileron, rotor, and elevator during the bank turn. So that's it for this lecture.